Hello, I'm Jeff Boyd. In this video, I'm going to show you elementary waves. You'll be able to see them with your eyes. We start with the idea of a resonant cavity. If I blow across the mouth of this bottle, it produces a certain sound, the wavelength of which exactly fits as a standing wave inside this cavity. If the wind from my lips produced a slightly different sound with a slightly longer or shorter wavelength, it would die out inside this cavity and you would not hear it. Now we shift to a slightly smaller cavity, which when I blow across it produces a different sound because it has a shorter wavelength that prospers inside the size of this cavity. The idea is that the size of a cavity causes certain wavelengths of sound to prosper and others to die out. Now that same idea pertains also to light resonant cavities. We will pretend that this is a light resonant cavity lined with mirrors and extremely small. Now obviously scientists wouldn't really use a cardboard box, but there are all kinds of ways today to make a micron size cavity like what I just described. We're going to put an excited atom into this cavity, and the crucial question will be, how long does it take before the atom stops being excited? But we're getting ahead of ourselves. What is an excited atom to begin with? Let's say that this is an atom in its ground state. We shine an intense light on it, and the energy of the light kicks an electron to a higher orbit, to a higher energy level. We then call it an excited atom, which we will symbolize by making it red. Now the atom wants to return to the ground state. The electron wants to go back to its ground orbit and lose all that energy, and in the process a photon will be emitted, and that photon has a certain amount of energy. The amount of energy in a photon corresponds to a wavelength. The more energy, the shorter the wavelength. The less energy, the longer the wavelength. So that's what an excited atom is. The atom will fall back to its ground state and become not excited at random. But in nature, there's a certain average amount of time that takes. We're going to compare how long it takes for the atom to fall back to the ground state in nature versus inside a light resonant cavity. So let's imagine that we're going to put this excited atom inside this box and time how long it takes before the atom falls back to its ground state. Now, there are two different answers to that question depending on the size of the box. In some boxes, the atom will fall back to its ground state hundreds of times faster than if it were outside the box. In other boxes of a different size, the atom will be inhibited and it will take 20 times longer before the excitement leaves the atom and it falls back to its ground state than if it were not in the box. So how does this work? How is it that some boxes seem to make the atom feel welcome and other boxes the atom feels unwelcome? Remember how I said that when the atom falls back to its base state, it will emit a photon of a certain energy, which will correspond to a wave of a certain wavelength. Now the question is, how does this wavelength fit into the resonant cavity, which is a box lined with mirrors? If the wavelength is such that there's a whole number of waves, then the wave will resonate and become a standing wave of increasing intensity, and it turns out that the electron will more rapidly fall down to a ground state, and a photon will be emitted. If, however, the wavelength of the wave is slightly wider or slightly narrower than the width of the resonant cavity, then the atom will act very differently. it will take 20 times as long for the atom to fall back to its ground state inside such a box as it would if it were not in the box, simply in nature. How then do we relate these three variables? The amount of time that the atom takes to stop being excited, the wavelength of the wave, and the width of the cavity. Apparently, the atom somehow knows something about the width of this cavity before an electron falls back to the ground state and a photon is emitted. I mean, if it didn't know that in advance, then the electron would fall back to the ground state at random and a photon would be emitted, and then it would discover that it's the wrong size box, and then what would it do? The photon comes back into the atom and the whole thing goes backwards in time and the electron jumps up back where it was? That makes no sense. What does make sense is that somehow this wave determines when and how welcome this photon is going to be when it comes out of the atom. Now the wave can only do that if the wave is real and exists prior to the emission of the photon. This wave, which is sometimes called a mode of the box, has got to be a real thing that exists inside the box before the atom releases its photon and falls back to a ground state. So what is this wave? It lives in this box apparently 24 hours a day, 7 days a week. This is what we call an elementary wave. Elementary waves live in this box 24 hours a day, 7 days a week. Now we could package it up and ship it to you so you'd have your own elementary wave, but you don't need this box. Elementary waves are everywhere. They're coming off my skin, going up in this direction, and photons from the light are following them back, which is why my skin is illuminated. Elementary waves are coming out of the camera and coming to this black felt behind me, and photons from the felt are coming back into the camera. Do you see the common theme here? Just as this elementary wave stimulated the emission of a photon from this excited atom, similarly, elementary waves from this camera stimulate the emission of photons from this black felt, which follow the waves backwards into the camera. Now you might say to me, my goodness, that is certainly an amazing camera to put out that much energy. But that is to misunderstand the nature of elementary waves. They are different than any other waves. These are something fundamental to the makeup of the universe. These particular waves do not convey and do not require any energy. So although they stimulate photons to be emitted and electrons to be emitted, they do not do so by means of energy. Elementary waves are, believe it or not, coming out of the retina of your eye, going to the computer screen that you're looking at, and photons from the computer screen are following them back. So there you have it. I've shown you elementary waves, and I told you I would show you waves you could see. Not only can you see that, but in addition, you wouldn't see me at all if it weren't for all the elementary waves involved in that process. Thank you.